it's very simple and straightforward to find the solution of the different profile and the location of the reaction sheet, simply by using the fact that YF is 0 on one side, YO is 0 on the other side. What if the Lewis number are not 1, and you want to find as a solution? Then we cannot use clearly the coupling function. Oh, come on. We cannot use the coupling function approach, and so, but we can construct some jump relation across the reaction sheet, something like what we tried to do in premix flame, but of course it's different because of the nature of the problem. The diffusion flames are different. So the first thing is that we can establish we can assume on physical ground that all the variables, YF, YO, and the temperature must be continuous at the reaction sheet, something that we have in fact seen before when we dealt with the case of unity Lewis number. And then we know that YF is identically 0 in the oxidizer region, and YO is identically 0 in the fuel region. Okay, so now suppose that you construct the combination of YF, YO, but now the Lewis number are not 1. So of course they appear here, and so in principle I cannot solve this equation because the variable here and here are not the same. So it's not a differential equation to solve. But I can integrate this relation across the reaction sheet, right? In other words, I integrate it from XF minus to XF plus, right? One side of the reaction sheet to another. So if I integrate once, this, since this is these variables are continuous, that contribution is 0. And the only contribution non-zero come from here. And when you integrate once, you get the derivative, or the fluxes. So the flux of the fuel multiplied by the reciprocal of the Lewis number is equal to 1 over nu, the Lewis number of the oxidizer to minus 1, the flux of YO, which is this part of the relation. In other words, those two fluxes are related. In fact, they are exactly in stoichiometric proportion. Now, the same thing I can do if I use a different combination, which is the temperature plus YO. And if I again integrate across the sheet, I get that the flux in energy, or the temperature, is related to the YO, but of course also related to the YF. So this is another relation that I can derive, okay? And it turned out that that's all I need. It's sufficient. In other words, unlike in the premix case where I also needed to obtain what is exactly the net flux from the internal structure, here I don't need that because you see the problem is that involve 3 differential equations, second order. So in principle, it's a 6-order problem, right? Second order, second order, second order. 3 equations, 6-order problem. Now, of course, there are 6 boundary conditions, 3 on one side, 3 on the other. But since I introduce a discontinuity at the reaction sheet, then I need also 6 conditions at the sheet. Well, in fact, I have 7, because one of them is needed, extra condition is needed to determine the location of the sheet. So here are the 7. This equal to 0 is 1, 2, 3, and then 4 or 5. Those are only 2 relations, so 5. But then, since YF is identically 0 on one side, YO identically 0 on the other side, I have 2 more conditions, which is 7. And so I have exactly the right number of equation and condition that I need, and we can now solve the problem. So here it is. We solve for YF, we solve for YO, where we satisfied continuity already. Now, if we impose this condition, which is the relation between the flux of fuel and the flux of oxidizer, which again, as I repeat what I said before, since one of them is 0 on one side, the YO is 0 on the other side, that statement is that the flux of fuel from one side equal to the flux of oxidizer, the other side, with the coefficient, meaning that they are in stoichiometric proportion, right? Because you have the nu here that appears, right? And so that condition immediately gives you an expression for the location of the reaction sheet, which is, if you set the Lewis number equal to 1, then you obtain exactly what we have derived before. So, of course, now the location of the sheet depends on the oxidizer Lewis number, okay? And phi is the same phi as we had before. The next is we can solve for the temperature. And again, we have this relation. And if we use the flux relation, we can obtain the flame temperature. These two relations have, the only thing that we have used here is that the solution is continuous at the sheet, and the value TA, I just called it the temperature of the flame, but I don't know what the value is, and so that relation gives you exactly the expression for it. And of course, when the Lewis number is 1, it reduced to the previous relation. So basically, okay, before I go to the next one, let me just add here an interpretation. We have noted, we have seen that the solution in this one-dimensional problem, right, when the Lewis number are not equal to 1, depend only on the oxidizer Lewis number. I mean, not the profile, but really the location of the sheet, as we have seen here, and the flame temperature, okay? And the reason for this is because, you see, the fuel is supplied with the stream, and the oxidizer have to diffuse against the stream. And so the position of the flame and the temperature of the flame is more sensible to the oxidizer, which has to overcome the convection and diffuse towards the reaction sheet, right? Okay, so now we can, what I have done here, I just tried to generalize the relation if the sheet is not planar, as we have done now, but is not highly curved. It's not very wiggled, right? And so if the curvature is weak, then what we basically what we see is that every segment, it's almost like a planar flame, but which can be done systematically from the equation. In other words, it's not an assumption. It's just, I'm just giving you the answer in a quick way and interpreting it. But the fluxes that you have in those relations need to be the flux in the normal direction, clearly, right? And so this is what is described here. So again, this jump relation across the reaction sheet tells you that the temperature and concentration are continuous at the reaction sheet, that the fuel and oxidizer are completely consumed, that's the last relation, and the middle one, that the net fluxes are diffusive, and that the diffusive flux of the fuel and oxidizer are in stoichiometric proportion. Now, the next problem I want quickly to discuss is the Burke and Schumann problem, which was, as I said, as I said earlier, was discussed by Burke and by Schumann in the late 1920s. And here is the problem. The configuration is such that you have two coaxial tubes. So these are axisymmetric, two cylinders, if you like. And the fuel is supplied in the center, the oxidizer from the outer cylinder. And the outer cylinder has a radius B, and the inner cylinder has a radius A. Okay? And what Burke and Schumann have assumed is that the flow coming here is the same. In other words, the fuel and oxidizer come at the same velocity, or at the same, or the flow rate is constant. And they further assume that the flow, so the flow is in the axial direction, and they further assume that the total mass flux, which is essentially the velocity multiplied by the density, is constant, remain unchanged. Usually it will be changed because the density changes with the temperature, and the temperature increases as a result of combustion. So essentially they have assumed a constant density assumption, even though it was not explicitly stated. Which it turned out that in diffusion flame, it's really less dramatic than in premix flame. But anyway, that's a side comment. In addition, they assumed that diffusion occurs mainly in the radial direction. In other words, diffusion in the axial direction is neglected. It's similar to, for example, boundary layer of jets, where you assume that most of the viscous diffusion is in the radial direction rather than in the axial direction. That's, of course, a simplification because the Laplacian in the equation reduced to only a term that contains radial derivative and no axial derivative. And then the problem reduced, instead of solving an elliptic problem, you're solving a parabolic problem. And that's a significant simplification, even numerically, but also analytically. So these are the main assumption, well, some of the assumption that they did. They further assumed, as discussed here, that the reaction rate is infinitely fast. So that's where this idea of an infinitely fast chemistry was introduced by Burke and Schumann. And actually it was a very wise, a very ingenious idea at the time, because it was not introduced as an asymptotic limit, but it was introduced more as an ad hoc approximation, but one with a lot of vision. So anyway, this is, in addition, they assume unity Lewis number. And so they, in fact, use this coupling function idea. But we know how to even avoid that if we are interested, as I've shown you just a minute ago, by satisfying jump correlation instead of coupling function. They have also assumed that gravity is not important in this problem. Gravity is usual, in other words, that buoyancy forces do not essentially distort the flame. You see, I did not discuss that parameter very much when we introduced dimensionless equations in general, but the important parameter is the Froude number, and the Froude number defined here is the ratio of inertial to buoyant forces, okay? And it's essentially the velocity squared divided by A is the radius and G is the gravity. So you see that if gravity, what you see is that flame heights are controlled by buoyancy essentially when the Froude number is small. When the Froude number is large, then, well, it could be large even because, either because gravity is small, which is in a microgravity environment, or because U is very large, right? So in other words, if the velocity is very large, then gravity doesn't have a lot of effect because the inertial forces are much more significant than the buoyant forces, okay? So anyway, this is the effect of gravity on the flame, and we are going to assume that gravity has no effect, as Burke and Schumann did. Now, the boundary conditions are going to be simple like this, that in the inner cylinder, there is fuel but no oxidizer. In the outer cylinder, there's oxidizer and no fuel. And then there is no penetration or no flux through the walls, which I have shown you. I have shown here in these two purple solid curves or lines. Okay, now these boundary conditions are consistent or are okay with the assumption that axial diffusion is negligible compared to radial diffusion. You see, if that's not the case, in other words, if you include axial diffusion in the problem, you cannot really impose boundary condition at z equal to 0, namely at this line here, right, as I specified here. In fact, you have to solve the problem all the way to sufficiently negative values of the axis z. Because if axial diffusion is important, then the fuel can, or the oxide can diffuse backward, right? There's backward diffusion. and it can go as far as the diffusion rate is, okay? So the assumption, these boundary conditions are fully consistent with the model that they have chosen. Okay. So they wrote the equation for the fuel, for the oxidizer. So you see their parabolic equation because convection is only in the axial direction and diffusion is only in the radial direction. And so one can, and the equation written here are made dimensionless using the outer cylinder B, the radius of the outer cylinder B as a unit of distance in the radial direction. So the radius go from 0 to 1, and C is the ratio of the inner to the outer cylinder, okay? So C is where the inner cylinder end and the outer cylinder start. And then the YF and YO were normalized with respect to the fuel mass fraction. So the fuel mass fraction is 1 in the fuel region, and the oxidizer mass fraction is just the ratio of oxidizer to fuel. Okay, so this is just a simple normalization. So you want to solve these two equations, and they have used, of course, their idea that when you introduce a coupling function, which they call psi, then the equation is a single equation for psi, which is conserved scalar, right? And then you solve this equation, and you set psi equal to 0 to obtain the location of the reaction sheet, as we did for the simple example. Of course, this is a more complicated equation, but one that can be solved, for example, by separation of variables. And if you use separation of variables, then you obtain that the solution is expressed in this form. It's an exponential, a decaying exponential in z in the axial direction, and this Bessel function in the radial direction. And the solution is an infinite sum, as you typically obtain in separation of variables. And the coefficients A0 and AN are determined by applying or satisfying all the boundary conditions. Okay, the details, I mean, there is nothing particular in the details, it's just that that's the form that you obtain. Now, if YF and YO equal to 0, which means psi equal to 0, the solution just is a relation between the radial distance and z. So it's a surface, right, in the space, right? And that surface is the flame sheet. And so, in fact, by solving this transcendental equation, what you obtain is the shape of the sheet. Of course, it is complicated because of the infinite sum, so let's just take a simple situation in which you, let's say, you truncate the series just for simplicity after one term. If you do that, then you get only those two terms, A0 plus A1 J0. J0 is a Bessel function of order 0, e to the lambda 1 square z, and you can determine the flame height. Well, it depends. There may be two situations, one that we call over-ventilated, one which is under-ventilated, which depend on whether the flame converge towards the axis or it diverges towards the wall, okay? And the height can be obtained in the over-ventilated case, the blue case, by setting the radial r equal to 0, because the height is going to be the value of z, right, when r is 0. So this is, I think, what is represented here. So you get h, the height is given by, I'm sorry, this is for the under-ventilated case. Okay, so you get a different expression for that case. And for the under-ventilated case, of course, you have to set r equal to 1, okay, which gives you the height. And so you can, in principle, obtain the height in that way. Okay, so it was important to bring that problem because, at least historically, it was the first problem that was solved by this idea of fast chemistry, and so I brought it up. The next one is a counterflow diffusion flame, which I have discussed, just the setup I have discussed earlier, and it's described here. So you have fuel emanating from negative infinity, oxidizer coming from plus infinity, and you're going to have a diffusion flame situated or at some position inside this flow field. Now, in general, the flow field, of course, vary as the temperature increases, the density increase, density change, and so there is an effect on the flow field, but we are going to assume, similar to Burke and Schumann and similar to other ideas that I presented before, we're going to assume that the flow field is not very much affected by the variation in temperature and density, and so we're going to assume a constant density. In this case, the flow field is very simple because that's the flow field of a stagnation point flow. In fact, it's the flow where viscosity has also been neglected. That's an ideal gas or potential flow. The potential flow is that the axial velocity is minus 2 epsilon r, and the transverse velocity is 2 epsilon x, and this is 2 epsilon y. The 2 is just there for simplicity because the solution will take a simpler form when you put a 2, but all it means is that 2 epsilon is the strain rate, okay, not epsilon. But okay, so this is a flow that has a constant strain at epsilon. Epsilon has units of 1/2. We discussed this before for premix flame. Now, if you want to take into account the density variation, you can, in fact, do a simple transformation of the coordinate and make a transformation from x to x hat, where x hat is a density-weighted coordinate. Well, then the problem is represented of x hat, but of course it's not the physical coordinate, so it's a bit a coordinate which is stretched or compressed depending on the value of rho. But I will skip that. It makes just things a bit more complicated, but doesn't change the ideas that I want to present. So we know the flow field is this, and since the flame is flat, then really the only convective, the only term in the convective term have only one contribution, which is x d by dx, because there is being flat, there is no variation of temperature and concentration in the y direction. Okay? So the problem is just these equations, and they were put in dimensionless form here using a unit length which is defined by the strain rate and the thermal diffusivity. Thermal diffusivity has units of centimeters squared per second. You divide by 1/2. That quantity has units centimeters squared. Take the square root, have units of centimeter. So that quantity has exactly units of length, right? And when you rewrite the problem in dimensionless form, the Dam-Kohler number that result here turn out to be inversely proportional to the strain rate, okay? So you increase the strain rate, you decrease the Dam-Kohler number. The other parameters are clear, are known, it's the same notation as before, Lewis number of the fuel, Lewis number of the oxidizer, and nu is the stoichiometric ratio oxidizer to fuel based on mass-based. Beta is the activation energy parameter, and here I have used I scaled the temperature not with respect to the unburned cold temperature, but rather essentially with the heat release. So temperature is scaled with this quantity here, okay? So roughly speaking, temperature will reach about 1 at the flame, and will go to some prescribed value on the cold end. Okay, so these are the equations. In the cold end, it goes to T naught. T naught is the scale temperature. Okay, so these are the equations that you want to solve, and we're going to write the solution. We will start with, there are two limits that I want to look at. The first limit is when the Dam-Kohler number is very small, goes to 0. That's not clearly the Burke-Schumann limit. It's the opposite limit. It's what we often refer to as a frozen flow. In other words, a chemical reaction is frozen. Frozen come from there. And so if D is 0, identically, then there is no chemical reaction. But you can still solve this problem. The temperature clearly will remain a constant throughout, but the concentration of fuel and oxidizer will vary because there is mixing. So this limit essentially tells you that the fuel and oxidizer mix through this entire infinite domain. And you can see here profile of the oxidizer, profile of the fuel for different values of nu, I believe. And this is presented here for equal Lewis number. In other words, the Lewis number of the fuel and oxidizer was assumed to be the same in these graphs. Okay, so this is an illustration of pure mixing. Now, in principle, one, not in principle, but this was done, in fact, one can extend this analysis by saying, okay, now the Damn-Coulomb number is not identically 0, but it's small, and so let's study how the effect of a weak reaction occurs. What you should get in this description, which I'm not going to show the detail, is how slowly the flame ignites and there will be a weak flame that develops, okay? Which is not the Birch-Schumann limit. It's exactly the opposite limit. The next case I want to show you is the Birch-Schumann limit, d going to infinity. And again, I left the Lewis number in general here. So, well, the method is, as I showed you before, you solve the equations for the fuel, for the oxidizer. Maybe I should just point out that the solution of this equation, this differential equation, x d by dx plus the second derivative, has solution which is an error function. And the error function is a well-known tabulated function. Essentially, it's a function that goes from -1 at negative infinity to +1 at positive infinity, okay? So it's a well-known function, and that's what you also expect, that in this case, the solution will have that similar form, except that now the fuel vanish and the oxidizer vanish at the position xf, and the position xf can be obtained from, again, this transcendental relation. If we assume that both the Lewis numbers are the same, then it takes a slightly simpler form. So let's analyze this case. So I've assumed that the Lewis number of the fuel and oxidizer is the same. So this becomes a factor 1. This is e to the 0, so it's 1. And so it's really only this expression equal to phi that result. And that expression can be simplified to the algebra. After some algebra, you get that the error function of the square root of the Lewis number times xf is phi minus 1 divided by phi plus 1. And here is the position of the flame as a function of this parameter phi, okay, which is the initial mixture strength. And that what you see is that when phi is equal to 1, you would expect the flame to be exactly at the stagnation surface, okay? At 0, it's not the numbers I know are now at 1. What is this? Yeah, when phi equal to 1, xf is 0, right? Which means it's exactly at the stagnation plane. When phi is less than 1, the flame is going to be on the fuel side, and when phi is bigger than 1, it's going to be on the oxidizer side. So in fact, we have a clear, I think it's summarized here somewhere. Where is, yeah, the reaction sheet is located along the stagnation surface when phi is equal to 1. It's located on the fuel side for a lean system and on the oxidizer side for wind. So we have a clear determination where the flame is. Note, by the way, that when the flame is on the fuel side, then the oxidizer have to diffuse through the incoming flow in order to reach the reaction sheet, right? Remember this? Here is the picture. So when the flame is here, the oxidizer has to diffuse across this flow, right, in order to reach the reaction sheet. Similarly, when the reaction sheet is here, the fuel has to diffuse through the incoming flow, in other words, to overcome this convective flow here in order to reach the reaction sheet. Okay? These are just representative solutions, and then this is just to show you that one can compute the flame temperature, and here is the point I want to make. So I have shown you the frozen limit, and in the frozen limit, the temperature remains, of course, constant. That's under the assumption that the temperature of the fuel supplied and the oxygen supplied was the same. Of course, it's not, then there will be heat conduction from one to another, but that's not an interesting question here. Okay, so this is the frozen limit, and the mass fraction of the fuel and oxygen just diffuse into each other, just pure mixing. So this is the limit of pure mixing. This limit is the limit of Burke-Schumann when D is very large, where all the fuel and all the oxidizer is consumed at a reaction sheet. And what I'm interested to plot here is the maximum temperature in the field, which is going to be, in the Burke-Schumann case, it's going to be the flame temperature, clearly. Right? Now, what happened when I increase the Dam-Kohler number from this end to this end? Or if I decrease it from the Burke-Schumann solution, I decrease the Dam-Kohler number, what happened? Right? Now, remember, decreasing Dam-Kohler number, it's like increasing the strain rate. Right? So what happened? Well, one possibility is that you're going to get a curve that connects the frozen limit to the Burke-Schumann limit, a curve like this, a monotonic curve. But you can also get an S-shaped curve like this red curve. Right? So you can have different possible response curves that connect those two limits. The red one is the more typical and the more interesting, because what it identifies is ignition and extinction criteria. So, for example, if you start from the Burke-Schumann limit and you start decreasing the Dam-Kohler number, right, then what you would get is that it's no longer a reaction sheet, but there will be some leakage of fuel through the sheet on one side, some leakage of oxidizer on the other side, small amount, but they will leak through, and the flame temperature will decrease slightly from the adiabatic temperature. And the more you decrease the Dam-Kohler number, the larger the leakage and the larger the deviation of the flame temperature from the adiabatic value. Up to a certain point where you expect that up to a certain point where you see that there is no solution which is a strong burning, and the solution have to drop to one which is very near the frozen limit. And that corresponds to extinction. And on the other hand, I can start with the frozen limit, increase the Dam-Kohler number up to a point where there is no more solution which is weak burning, and the solution suddenly jump up to a very strong burning, and we refer to that as an ignition. So the S-curve has this behavior or this phenomena of possible ignition and extinction. And typically in problems like the counterflow, in many of the fusion flame problems, the response curve is more like the red curve rather than the blue curve. Okay? So it's typically an S-curve shape, and the S-curve had this ignition extinction behavior. Okay. And this is just to recall that the Dam-Kohler number is inversely proportional to the strain rate. Okay, now I want to, I'm not going to go through the analysis here in detail, but I want to just address few quick points that appear in some of these transparencies. And this is the discussion that or the comment I made earlier today, that in fact, in order to accept the Burke-Schumann solution, we really have to analyze the structure of the thin reaction zone. And so this can be done, in fact, in general. And so I wrote here the general equation, but I will skip that. The focus really is on only these three equations that involve temperature, mass fraction of fuel, mass fraction of oxidizer. And this picture just tells you that we can do it in general for a sheet, not necessarily planar, but even one that is curved, if you write this equation by using the normal coordinate to the sheet and the tangential one. So if you do that, then the gradient will have a normal component and a tangential part, and well, that's details again. So the main idea is near the sheet, which is described by n equal to 0, right? The coordinate n is normal to the sheet, so n equal to 0, it's at the sheet. Then you want to zoom on this region. You want to stretch it. So when you stretch this region, that's what you do. You write n is equal to some epsilon eta. And epsilon is a small parameter that at the moment I didn't define, I didn't determine, but it will be determined through the analysis. Now we know that near the sheet, the fuel and the oxidizer, there should have been a YF here. The fuel and oxidizer are nearly 0 because in the Birch-Schumann limit they are totally consumed, and so they should be nearly 0 or small, and so they are expanded as epsilon times some quantity. And the temperature is near the adiabatic temperature of complete combustion, and so it's perturbed as adiabatic temperature plus a perturbation. So tau represent the temperature, and the little yf, little yo represent the fuel and oxidizer. And now if you substitute this in the equation, similar to what we have seen in premix flame as well, usually in the thin reaction zone, the important thing is diffusion compared to convection. Convection is usually negligible compared to diffusion. And so the diffusion terms survive with the 1 over epsilon coming from the stretching. There is 1 epsilon that comes from the tau, epsilon square from the second derivative of n, and so one of them cancel and you are left with 1 over epsilon. And then on the right-hand side, you have epsilon square, 1 coming from the fuel, 1 coming from the oxidizer. So in principle, that gives you a balance that the second derivative of tau, which is the heat conduction, right, is d, which is very large, epsilon cube, epsilon is small, and then I didn't say anything about activation energy. Let's say it's finite for now, because in the Birch-Schumann discussion, that is not a parameter of importance. And so that's just a finite factor. So in the Birch-Schumann limit, the small epsilon need to be the Dam-Kohler number raised to the -1/3 for these two terms to balance, okay? And then the structure of the reaction zone is one that gives you that the second order derivative of tau is proportional to YF, YO. And so this is essentially the structure of a Birch-Schumann solution. And now there are some details here, but they are not really written down explicitly. The idea is that you can write a similar equation to that for YF and a similar equation to YO, of course, right? Because they all have, or you can use a coupling function for those variables, because in the absence of convection, you can always write a coupling function. And these are the coupling functions. So if you solve these equations first, because they are simple, they are equal to 0, then you can find the relation between YF and tau and YO and tau. And if you put it together, you're going to get a single equation for tau that has YF and YO. So you see YF and YO are related to tau by linear function, if you like. And through a simple transformation, not so simple, but through a transformation, one can rewrite this problem as a canonical problem that has no parameter in it whatsoever. That is what the equation is. Now, this equation need to be solved over an infinite domain, -infinity to +infinity. -infinity corresponding when you get closer and closer to, let's say, the fuel side, then +infinity, you get closer and closer to the oxidizer side. What are the boundary conditions? Well, you obtain them by asymptotic matching. I mentioned earlier this week the general idea of that. And so in this case, turned out that they have to go to the slope has to go to ±1. So this problem cannot be solved analytically, but you can integrate it numerically. Since it does not have any parameter, you only need to integrate once and for all. And in fact, you can show by numerical integration that the solution always exists, and the solution is such that it connects smoothly those two slopes, which is exactly which is what, let's say, if this is the temperature profile, then it connects this slope with that slope. In other words, it makes a nice, smooth solution of the temperature through the reaction sheet, right, through the reaction zone. Essentially, what this says is that a solution always exists, and therefore the Birch-Schumann solution is it's a good solution in the limit when the Dam-Kohler number goes to infinity. Okay, it's a solution that is always exists. Now, it was later on found primarily by the work of Lignan in 1974 that a more powerful expansion is to use the activation energy parameter rather than the Dam-Kohler number. But in fact, you need both. In other words, you need what we call a distinguished limit. And the difference between the two, and I'm not going to go through the details, the difference between the two is that in addition to what we have seen before, then you get an additional exponential dependence on temperature in this reaction diffusive, in the reactive diffusive balance that occur in the reaction zone. So now this is the equation that you have to solve. And if you go through some of the similar algebra that I did earlier, you end up with a problem. Again, it's a canonical problem, but now it depends on two parameters, delta and gamma. Okay? It depends on these two parameters, and this is the canonical problem that you have to solve that describes the reaction zone, the variation in temperature in the reaction zone. Now, again, it has to satisfy matching condition, and these are the matching conditions. The slope has to go to plus or minus 1. Why 1? Because we made transformation to make it or bring it to a canonical form. That's all. Otherwise, it was a different slope. As you could see here, it was some coefficient A and B that were related to the slopes of the temperature and the mass fraction, etc., from the solution outside the reaction zone. Okay. Before I tell you the answer of this problem, let me tell you what these two parameters are. And in fact, it's written here, well, delta is written here. Delta is effectively a reduced Dam-Kohler number. So it comes from this distinguished limit here, but it comes from more or less from this distinguished limit here. So anyway, it's related to the Dam-Kohler number, but being a parameter, it can vary. So if delta go to infinity, 1 over delta is 0, e to the 0 is 1, and that exponential is absent, then you obtain exactly the previous problem. So delta go to infinity is like the infinite Dam-Kohler number. It's like the Birch-Schumann limit. But delta can also take values that are not infinity, because delta is scaled such that it's a finite number now. It's a finite parameter. And so any lower value of delta is going to be representing a Dam-Kohler number which is not infinite. It's large, but is reduced from infinity, is less than infinity. So in a way, we're going to try to see if we can establish here a part of the solution of this S-curve which we were not able to obtain in the Birch-Schumann limit. Okay, and so delta is essentially like the Dam-Kohler number. Now, gamma, I didn't write it here. But I discussed it earlier before. It was exactly the same gamma, and that's why I introduced it then. It's a parameter, it's a heat transfer parameter that tells you how much more heat is transferred to one side of the reaction zone than another. And we have seen that it's also related to the initial mixture strengths. So it depends on the conditions of the boundary conditions, if you like, of the problem. And so what's interesting in this equation, that it's different than the one that we discussed before, that, as we are going to see, there is not always there are solutions. Solution exists, but only for a certain range of delta. And so we start with the symmetric case when gamma is 0. You see, when gamma equal to 0, the problem is symmetric with respect to zeta, essentially. And so here are solutions for gamma equal to 0. So the solution goes from large in the yellow, purple is delta equal to 1, then smaller and smaller values. So what you see, let's focus on the red one, because the purple one, the counterpart of it is not shown. So if you look at the red one, which is the value delta equal to 0.856, in fact, there are two solutions. There is one here and one here. And if you look at the blue one, again, there are two solutions, one here and one here. And the black one, there is a single solution. Okay? And then if you try to lower delta below this delta critical, there is no solution, the problem. The boundary value problem has practically no solution. Not practically, has no solution, sorry. Now, you may ask me, what about this larger value? Well, there are solutions. There will be another one for the purple, but it's going to be here outside the range, so it's not really graphed and so on. So, in other words, what we have seen here is that for a given delta, there are two solutions. The same happen here when gamma is not 1, but it's 0.4. It may be a little more obvious. Here is the two solutions for the value 0.85. Here are the two solutions for 0.829. And then here is the critical value. The solution is unique. And so this is, in fact, shown in this part of the S-curve. In other words, we are in a range here. You see, as you reduce D, which is, we reduced it by changing delta, we have two solutions, but when delta is bigger than some delta critical, then there is no solution. I'm sorry, when delta is less than some delta critical, there is no solution. For delta bigger, there is always two solutions. So in fact, we were able to construct the part that include the extinction value, and in fact, the asymptotic description give you an expression for de-extinction. Okay? So the limit is richer than the Birch-Schumann limit in the sense that as you can describe a wider range of the Amkoller number, in fact, from infinite all the way to extinction. And the flame temperature, which is related to this, the flame temperature, which is related to this phi, or this tau here. Remember, tau was a deviation of the temperature from the adiabatic temperature. And so the maximum value of tau gives you the flame temperature. And so clearly, that tau will decrease, right, as you move further and further away from the Birch-Schumann limit. Okay? And so this shows you that when delta is bigger than delta critical, you also have a significant amount of leakage of fuel and oxidizers through the flame. And so I gave you a description of that before, but now we were able to, in fact, compute them. So, for example, for gamma positive, S1, this represents the fuel leakage. And so you see for different value of gamma. And so for gamma equal to 0, and this represents the oxidizer leakage. So for gamma equal to 0, the two curves, the two black curves are the same because of the symmetry of the solution. But then as you increase gamma, you have more fuel leak and less oxidizer leakage. And when gamma is negative, you just flip them over. This is the oxidizer, this is the fuel. So essentially what we have described is, again, that we have this S-curve, right? We were able to describe this whole turning part of the S-curve, including the extinction point and the extinction condition. Okay, so there is more leakage and the flame temperature drop here from the adiabatic value. Okay, so to summarize here, essentially, one can generalize the Birch-Schumann solution by adopting exactly the same conditions for the fluxes and the continuity of the different variables across the sheet, but allowing for a small amount of leakage of fuel and oxidizer, which computed from these functions that I just showed you before. And it's small because you see that the fuel and oxidizer leakage is multiplied by beta minus 1, which is the small parameter, the activation, the inverse of the activation energy. And so this is essentially something about the structure of the solution. I want quickly, before we take a break, go through the notion of a mixture fraction. And for a, in principle, the mixture fraction is defined as the fraction of the total amount of material present that came originally from the fuel stream. But, and one can define it for a more complex system that involves many species. But in our case, since we are focusing on a simple reaction that is fuel plus oxidizer go to product, then the simple definition is this. Z is equal to this ratio. And so you see very quickly that on the fuel side, since there is no oxidizer, okay, first let me explain. YF1 and YO2 are the mass fraction of fuel in the fuel side and the mass fraction of oxidizer in the oxidizer side. Those are like the boundary condition. Okay? So now on the fuel side, there is no oxygen, and so YO is 0, and so Z is equal to nu YF plus YO2, which is exactly what's in the denominator, so Z equal to 1. And on the oxidizer side, there is no fuel, so this is 0. YO is equal exactly to YO2, and so Z equal to 0. So the mixture fraction is usually defined such that it's 1 on the fuel side, 0 on the oxidizer side. Okay? So that is the definition, and that follows what you had before. Now, if you, the other thing about the mixture fraction is that it is a convenient parameter, as we shall see, for unity Lewis number. So let's first assume that the diffusivity of fuel and oxidizer are the same, okay? Which is not to say that the Lewis number are necessarily unity, but it means that the two Lewis numbers of the fuel and oxidizer are equal. The next step will be to assume that they're 1. So if they are equal, it means that you can combine those two relations, and Z is essentially, which is, here is a definition, it's essentially like YF minus YO. That's a constant. So when you take derivative, it's like a coupling function. So it's one of the coupling functions. Okay? So if it's a coupling function, then when you construct the equation for it, it will have a 0 on the right-hand side. In other words, it's a conserved scalar. Okay. So the equation for Z is just convection diffusion equal to 0. Now, since you know what Z is, you can very easily obtain what is the value of Z at the reaction sheet. That's when the fuel is 0, the oxidizer is 0. So that's what we call Z stoichiometry. Z stoichiometry is where the reaction sheet is, or it's the value of Z at the reaction sheet. And so it's equal from this relation to YO2 divided by the sum. So that defines the stoichiometric surface. Now, since from that expression, we can also obtain an equation for YO expressed in terms of Z, an equation for YF in terms of Z. Because where there is oxidizer, there is no fuel, so this is 0. So you solve for YO, and you obtain this straight line, which is a simple line. It's a straight line. It's a linear relation with Z. And where there is no YO, there is only YF, and you can solve for YF. You obtain a linear relation. So YO and YF, expressed in terms of Z, are simple linear relation. Now, if in addition you assume that the Lewis number is 1, well, you can also show that this is just to say that one can show the temperature is also a function of Z. And if you use the coupling function HF and HO, which is a combination of temperature and mass fraction, you can also express those two complex functions in terms of Z, and therefore express the temperature in terms of Z. So anyway, you can express the whole field in terms of this mixture fraction, right? And they take very simple linear form. Now, in a particular problem, of course, Z is related to the coordinate system or the configuration that you're solving. So for example, if you are interested in a stagnation, so you see, well, let's finish this. So if you're interested in stagnation point flow, let's say, then the equation is, as we have seen before, is 2 epsilon x dz dx plus the diffusivity times the second derivative. And you can solve this equation for Z, which is in terms of the error function. So what you have, if the problem is a one-dimensional problem, vary only along one direction, then the equation for Z, or there is a relation between Z and the coordinate. In other words, Z is nothing more than either expanding or compressing the coordinate. So in this case, it's like taking the infinite domain from negative infinity to plus infinity for the stagnation point flow and reducing it to the coordinate of Z from 1 to 0. So it's like a transformation. But in more general problems, that's not necessarily the case, because in multidimensional problem, then if you decide, or you have to decide in which direction you are doing this transformation to Z. Normally, you do it in the normal coordinate. And in fact, if you do it in the normal coordinate, what you will see is that when you derive your equation for the reaction zone, then in front of the diffusion term, you're going to have this gradient of Z squared. And that term in dimensional form have units of 1/2, and it's known as the scalar dissipation rate. So it's a quantity which is denoted by chi, and in fact, it's related to like an inverse diffusion time. So that's going to be effectively like changing your Dam-Kohler number, and oops, well, no. Well, okay, let me just finish it without the transparency. So essentially, what we have seen is that when you decrease the Dam-Kohler number below some critical value, extinction would happen. And so you can relate the extinction value to this scalar dissipation rate, okay, chi. And so that will be essentially the equivalent or the use of this mixture fraction variable. In other words, what you do, you change your normal coordinate to this mixture variable coordinate, okay? The problem is that it's only good when the Lewis number are unity. Otherwise, the definition of Z does not really, it's not totally consistent to use Z and allow for, variable diffusivity. So Lewis number not 1. So there is some use to that mixture fraction, and a lot of people like it because, of course, it simplified the problem greatly. With that, I will stop here, and after the break, we're going to move on into droplet combustion and spray.